this a little bit. I have a random variable or random vector, doesn't matter. I have its density function, and I wish to estimate this. Okay. Direct simulation or crude Monte Carlo would be I sample from f to get ID copies of x, then I do Monte Carlo. But this may be difficult because sampling from f is hard or variance is too big. Okay. Then we seek another random variable or another distribution. We do the following. Okay. This line is very important and it's very simple. Okay. Mu is equal to EHX, which is the desired target, that is equal to this integral, right? Hx times fx dx. Okay, no problem, right? Let's divide g and multiply g, no problem. Divide g, multiply g. You see why we require this condition? That whenever g is 0, f is 0, we can't have a positive number divided by 0. So if you have 0 divided by 0, we're okay. But we can't have a positive number f divided by g, which is 0. So we blow up. So because we divide g, right? Okay, so hx, fx divided by g, multiplied by g, okay. What do we have here? What do we have here? Consider this as a new function, grouping everything together and regard g as my new density. So let's say g is the density of some random variable y. So g here is a density of, x have density f, and g and y has density g, because x and y are different, right? This can be regarded as an expectation of this function of a y, right? Because I have the density of y given here. So let me repeat that, okay? Initially we have this mu equals EHX that is given by this formula, where x have, the PDF, which is given by f. We divide g, we multiply g, we regard g as a new density, and this term as our new h function, call that h tilde if you wish. Okay? So because a y random variable has this density g, we can reinterpret this as an expectation of whatever h function we have here of y. Okay? Right? So that's this, right? So this whole thing, oh yeah, and we call f over g the L function because it's the likelihood ratio. Likelihood is the density, right? So it's the density ratio, right? It's the density of f divided by density of g. So we give it a new name L here. So this new random vector, random variable follows the distribution g, and L is called the likelihood ratio. So okay, this line is everything. Initially, if we do Coulomb to Monte Carlo simulation, we would do what? Generate x according to f, generate ID copies, get hx, average. Coulomb to Monte Carlo. With this new notation, we don't have to do that. We can generate ID copies of y. How? According to g. Right? Using g to generate ID copies of y, and compute hy, ly, and generate many copies and average. Monte Carlo. Question? You're okay? Right. So this estimator is unbiased because the expectation of it is equal to the mu. Unbiased, right? So this is the so-called importance sampling estimator. Is hy times ly, or equals h small f divided by g, where y follows the g. Of course, we can't choose arbitrary g, right? We have to choose g wisely, so this becomes easier, right? Remarks. Both h and hl are unbiased estimator. Basically, both this guy, hx, and hy, ly are unbiased estimator because they have the same expectation. Okay? We're doing this, we're going through this trouble because we hope that this importance sampling estimator, the ISE, right, called importance sampling estimator, has a smaller variance than the crude Monte Carlo estimator, right? CMC is crude Monte Carlo estimator. We hope that we can do better. Otherwise, why would we go through this trouble, right? This approach is called a change of measure, change of probability. What have we changed, right? Instead of generating x using probability density function f, we're generating y using a different probability density function g, right? We change the probability measure, right? In previous example, you know, the dart should be uniform in a big square. We change the measure so that our new dart is only uniform in a smaller rectangle and zero elsewhere. So we change the measure. We change the way random variables are distributed, right? Same idea works for discrete random variables having probability mass functions. Example time. Okay. Let's say our objective is to estimate theta that is equal to the probability a normal random variable, standard normal, is greater than 20. We know that is very, very small, right? So, I mean, you know, this general argument gives us a way to estimate expectation, but we all know that, you know, probability is expectation, right? How do you estimate this probability? You just estimate the expectation of indicators, right? This is just an example of the previous page, okay? Basically, put this into our framework, this is the thing, right? This is the EX, the E of some random variable. If you do crude Monte Carlo, you're going to suffer. Okay. All right. Basically, you need to generate at least, you know, n equals 10 to the 89 to see sort of one indicator equals 1. Okay. Let's do the following. Let's write it out. Okay. The expectation of the indicator is equal to, you know, this is the expectation, right? Let's condition on the value of x, right? This is an h function of x, so it's going to be h function of a small x times the density function of x, and then there's a typo here. There should be square root here. If you're familiar with normal distribution, this should be square root, right? This term is 1 over square root of 2 pi, right? So this is my f, so this piece should be my f, right? This piece should be my h, this part. So I have h here, I have a f here, which is consistent with this, right? Got it. It's true. All right, I'm having an example here. What do we do here, right? Let's pick a g. Let's pick a g. So I mean, many g's you can pick, right? Let's just pick some easy one, right? Let's pick a normal g. So this is the g. Again, there's typo here. Square root of 2 pi, square root of 2 pi everywhere. Square root of 2 pi. Everything should be square root of 2 pi. Whenever you see 2 pi is square root. Okay. Alright. So let's divide and then multiply this g function. This is g, this is g. Okay. G. What is g? G is a density function for a normal random variable having variance 1 and the mean mu. Easy, right? You can see it's very similar to f, except that here in the exponential term is x minus mu. And mu is something we will determine later. We will determine a mu so that this event is no longer rare. Alright, so cancel out the terms, right? So do some simplification. So keep the g here. Again, this is square root of 2 pi. And cancel out some terms, and combining the exponential, you see this thing. This is the adjusted new h, right? This term, highlighted in dark blue, is equal to this new function here, okay, of everything combined, right? That's this. Or, you know, finally, we're going to interpret this whole thing, this whole new formula, as the expectation of this function, right, this function, but for random variable x mu, a new random variable. You can call it y if you want, but I call it x mu because I'll have mu to be the index of this x, because mu is something we haven't determined, right? So eventually, this is the expectation of this function of some y. Here, this some y, we call it x mu. Question? So this is consistent with this, right? The whole function here, expectation, but a function of y, and y follows the g. Right? We're good? We're good? Okay. Let's take a look at this, right? What do we mean by this, right? Initially, if you wish to estimate this probability, you have to generate x, which is normal distributed between 0 and 1. So the mean is 0. It's really unlikely for x to be greater than 20. So this is gonna be bad. But look at this one though. If we have a good mu set up, we are able to generate not a 0, 1 normal, but a mu 1 normal. So this will happen from time to time. So what kind of mu to make can make this event no longer rare? What kind of mu? What value should mu be? Should mu be negative? I'm picking a optimal mu, a good mu, so that this event greater than 20 is no longer rare, right? What mu should we do? Negative? Positive? What value? How about 20, right? How about 20? Yes. Let's just do 20. Let's put mu 20. So if mu equals 20, half of the time this will be 1, half of the time it will be 0. Right? Half of the time this condition is met, half of the time not met. Okay? So go tilt the distribution of x to a new distribution so that we can sample more often in the important region. This is the important region. Why is the important region? Because we care about this region. Right? Okay. Choose a good mu to achieve a smaller variance. So first of all, the indicator, so this is the function, right? This is the whole thing. This guy is less than or equal to the right hand side. Why? I mean, left hand side is a random variable because it's a function of a random variable. And right hand side is just a deterministic function. Left hand side is always less than or equal to the right hand side. Doesn't matter what value x mu is. If x mu is smaller than 20, 0 less than right hand side. If x mu is greater than 20, this is 1 and this is negative. Right? If x mu is greater than 20, this term is less than e minus mu 20. So left hand side less than right hand side all the time for any value of x mu. Okay. So we have an upper bound of this random variable, and it can be proved that all we need to do is to minimize this upper bound to get a optimal mu. So if you minimize the upper bound, you minimize the variance. How do we minimize the upper bound? Well, you just simply do a first order condition. You can actually it's not you don't even have to do that. You can see that this whole thing, this right hand side is decreasing in mu. Oh, sorry. It's actually a quadratic function, so you have to take a first order condition, right? It's decreasing in the exponential term. So all you need to do is to minimize this exponential term. It's a quadratic function, so it's easily observed that this quadratic function is minimized when mu is 20. You can just do that, right? Minimizing this thing, and the minimizer mu star is equal to 20. So basically, it's optimal here to do x sub 20, which follows a normal distribution with the mean 20 and the variance 1. Intuition here, with the mu equals 20, the event is no longer rare. The raw indicator, the raw multicolor estimator alternate between 0 and 1, yielding a large variance, because 2-point distribution is really not good. You may argue that, oh, the variance is not too bad, the variance is less than 1, right? Because the variance of a Bernoulli random variable is p times 1 minus p is less than 1. But the mean is less than 1. The mean is also very small, right? So what we should worry about is the relative variance, right? The variance is not big, but compared to the mean, it's big. Okay? But the important sampling does the following, right? The value is 0 in this region, right? Because, if you sample from x mu or x20, sample from x20, which is the normal distribution with mean 20 and 1. If you see less than 20, you got 0 because you have the indicator. But if you see greater than 20, this indicator becomes 1. The value you see is going to be this function. But in this region, this is also very small. So you don't really have a big fluctuation between 0 and 1. 0 and 1 are very different. But 0 and a small number are not too different. Right? Let me repeat that. The raw Monte Carlo estimator alternates between 0 and 1. So 2-point distribution always has a large variance. Two distinct, right? 0 and 1. But important sample estimator. You sample from x mu, x20. And if you see x20 is less than 20, which is half probability, right? Probability 50%, you're gonna see 0, because the indicator becomes 0, whole thing is 0, you return 0. If you see x20 is greater than 20, you're gonna see this piece, because this first term is 1. But the second term is very small. Second term is just e to the 20 times x mu plus 20 squared over 2, and it's very small, right? Because the exponential term is very negative. So you don't really have a large variance. You continue to do this in the independent runs. You will see either 0 or small number, 0 or small number, so the variance is minimized. Is variance reduced, right? Variability is reduced. Again, right, the main intuition is that we make the rare event happen more often. So the rare event happens 50% of the time after we have shifted the expectation of this more random error. This is the first example. You can check this. You can do a simple simulation study by using my alternative simulation. You will see that you can get this number pretty quickly. With this number. You don't need that many samples. You can sort of get at 2.7 much quicker, way much quicker, right? Because if you do the crude Monte Carlo estimator, even if you do 10 to the plus 89, you probably have one sample. It's still pretty crude. It's 1 times 10 to the minus 89. But I want to estimate. I want a good estimate, right? Accurate estimate. I want to have a good number here, right? You try that. This is just a toy example.